Welcome and hello. This is a video exercise in HEC RAS, and in this exercise, I'm going to be dealing with the current number and advanced time step controls. I'm going to build a simple model, run the simulation using the basic default time method, and then return to use and demonstrate the two advanced time step methods. So let me go ahead and show you what that means here. I've got HEC RAS up on the screen here. If I click into open up the unsteady flow analysis dialog box and then go options, computation options and tolerances, and then advanced time step controls tab, we have the three different options here. First, there's the default, which is the fixed time step or basic method. Then we're also going to look at the adjust time step based on current number, as well as using time series divisors. All right, so that's what we're doing in this exercise, as well as taking a look at that current number and how it is affected by different parameters in the model. Okay, so let me close this up, close this. Before we get to all that, we're going to go ahead and start from scratch, build the model, and then get to the actual simulation. The potential benefits to using some of these advanced time step controls is to improve model stability and to also reduce computation time. All right, so let's get started here. I'm going to start by clicking on Geometric Data Editor, and we actually need to create a project first. So File, New Project, okay, and then navigate to the directory you want your project to be saved to. Make sure to give your project a title over here in the left side, and then go ahead and click OK. All right, and then accept the unit system by clicking OK. If you don't already have the Geometric Data Editor open, go ahead and go Edit Geometric Data, where you can click on this button right here. Now let's go ahead and sketch in a river reach. So I'll just go ahead and single left click a few times. This is not going to be geo-referenced. And then double click at the end of the reach. I'm going to call this river and reach. Okay, I'm only going to have one river and one reach, so that's fine. Next, I'm going to define the cross section here. So I'll click on Options, Add New Cross Section. I'll start at the bottom of the reach and just say it's river station 0. So this will be 0, 0, and 0 for the downstream length. Next, I'm going to type in or paste in some numbers here for the station and elevation data. So I just pasted in some numbers that I had saved on my clipboard, which I copied in from Excel. All right, Manning's end value, I'm just going to type in some typical numbers here. And then the left bank station will be 100, and then right will be 250. I'm just looking at my data here. And then click Apply Data. All right, so this is the cross section of the downstream most location of the river reach. I'm going to go ahead and just make a copy of that and then create an upstream cross section as well. I'm going to say the upstream is 5,000 feet and then click OK. And then I need to do a few things here. 5,000 is the distance downstream. And then I also want to go to Options, Add Elevation, and I'm going to add 50 feet. So the invert goes from 80 feet down to 30 feet. Apply data, and then we can confirm those elevations. So 80 down to 30. All right. That's all I need to do here for the geometry file. So let me just go ahead and save that. Save geometry data. I'll just call this my base file for geometry. Next, let's go ahead and define some boundary conditions and unsteady flow data. So I'll go Edit, Unsteady Flow Data. You can also click on the button right here. Okay, let's start with the downstream end of the reach. That's at river station 0. I'm going to just type in the normal depth. This is a slope of 1%, so I'll just use that for the slope. And then upstream at the river station 5,000, I'm going to use a flow hydrograph. And to keep things simple, I'm just going to enter the data into the table here directly and use the simulation time, which means that this flow data will start at the same time that the simulation starts, so that those two files are synced up chronologically. All right, I have that data already saved on my clipboard, the flow rates. So I pasted them in here, and to get an idea of what that looks like, I'll click this plot data button, and you can see the flow just increases from 100 CFS at the very beginning, and then it ramps up to 24,000 CFS. Let's see what that does. All right, so I'm going to click OK here, and then File, Save Unsteady Flow Data. I'm going to call this 100-24K, just to represent the range of flow rates, and click OK. All right, so that's good. One more thing to the geometry file I wanted to do and forgot to do when I'm looking at my notes here is to add some intermediate cross sections. Typically, 5,000 feet is too far between adjacent cross sections. So let's just go ahead and interpolate. And then I'll say 500 feet, interpolate, and close. All right, great. And then we go File and Save Geometry Data. Alrighty, let's go ahead and click Run. This is our Unsteady Flow Analysis dialog box. We already saw this earlier in the exercise when we went to Run Unsteady Flow right here. Okay, I'm going to use this same unsteady flow file as the name of my plan as well, 100-24K. So I'm just going to paste that in here, and then same thing for the short ID. All right, next I want to check on geometry preprocessor, unsteady flow simulation, and post-processor. It's a 3-day simulation on a 1-hour time step. At least the flow data is on 1 hour. So I'm just going to use my January 2020, the first day of that month, and that'll go for 3 days. Okay, so I got that data right there saved. Below that, I'm going to just use the default computation settings, which is a 1-minute computation interval. And then the results here will write out at a 1-hour time interval. All right, so let's go ahead and save and then click compute. All right, so it looks like it computed. All right, we had a few warnings or error messages. I believe there's some instability between cross sections at river station 5,000 down to 2,000. So let's go ahead and take a quick look at what's going on there. I'm going to go ahead and view, and then let's take a look at the water surface profile, and then I'm going to go ahead and animate this and click play. So the water surface is increasing as the flow rate's increasing. That's to be expected. Now in the second half of the simulation, things get out of control, you can see. I'm going to take a look at the cross section at the upstream end of the reach while I'm here. So view, cross section, river stations 5,000, that's correct. Now let me just go ahead and animate that. So the water surface is increasing, day 2. Yeah, on the 3rd day, things go a little haywire. All right. The user's manual mentions that 2 ways to improve the stability of the model is to decrease that current number. Here's the equation for it right here, and it equals velocity. This is the flow velocity or wave speed times the time step, that's dt, all divided by dx, where dx is the distance between cross sections in the 1D flow or cell centers in the 2D flow. So we're going to be looking at this equation again when we make a few modifications. But what I want to do first is just calculate this current number for that last simulation, because it looks like even though it went unstable, we still had some results we could look at. I'm going to go up to Run and then Unsteady Flow Analysis. And then now in the options, I'm going to go to Output Options. And then over here, this third tab is Computation Level Output. I want to go ahead and check the checkbox to write computation level output. And then I also want to click this current number in the channel. Okay, I don't want to specify a specific time range, and that will allow the entire simulation to be written for these specific variables. Okay, so if I click OK and I want to see the results, I'd go View and then Unsteady Flow Spatial Plot or Unsteady Flow Time Series Plot. These are not available to me because I need to save and then run the simulation with those output options enabled, the ones that I just specified right here with this checkbox. Okay, so I'm going to click OK. Also notice that we now have a computation level output is on, so that's just a note. Let's go ahead and save and then click compute. Okay, so basically the same computation as before. Now, if we go up to view and then unsteady flow spatial plot, we now have a plot here where we can plot the variables for a specified reach. This is water surface elevation. We can also toggle on flow or current number. And then if we added more checkboxes to that dialog box just before the simulation, we could add more variables to track right here. There's also tabs here. We're on the profile tab. There's schematic plot and table plot, but I'm going to just stick with the profile plot for this exercise. Okay, so we don't really care too much about water surface profile. I'll go ahead and demonstrate it anyway. It's just going to increase. It's going to look a lot like what we saw earlier. So the line's slowly increasing, and then it'll start going unstable about halfway through the simulation. I'm not going to wait for that though. Let's go ahead and look at flows. So this is the flow rate. We can also run that simulation. And then what we're really curious about is that current number, which is this calculation right here. And as you can imagine, over the course of the simulation, the dt is not going to change, the dx is not going to change, but the velocity will increase as the flow rate increases. So let's go ahead and toggle on the current number now, and then reset the play bar and then click play. That current number is increasing from about zero point 0.6 past 1, past 1.5, and it's going to continue on until about 2.4, I believe. Yeah, I'm looking at my notes here. It starts at about zero point 0.4 and it increases to about 2.4. And as you can see towards the end of the simulation, it goes unstable. If we return to this calculation, we can manually modify what that current number is. Typically, the goal is to decrease the current number. So if we wanted to do that, we could increase dx, which is the spacing between cross sections in our 1D model, or we could decrease dt, which is the computational time interval. Let's go ahead and do that first one first. Increase the spacing between cross sections. All right, so minimize that, close that, close that. Back to our base geometry file. I'm just going to go ahead and modify the base file. I'm not going to save separate geometry files. It'll be fine. Let's go Tools. Let's go ahead and I'm going to delete the interpolated cross sections. Okay, so they're gone now. Let's go ahead and change it to maybe 1,000 feet between intermediate cross sections instead of 500. And then I'm just going to type in 1,000. Okay, interpolate and close. So now that we have doubled the distance between cross sections, we've doubled the denominator, and then that current number, which ranged from 0.4 to 2.4, is going to probably half and range from 0.2 to 1.2. Let's go ahead and see if that's really the case or not. So let me save the geometry file, go back, and then run this simulation once again. Okay, so I'm not seeing any instability. Let's go ahead and take a look at the results. So I'm going to go View, Water Surface Profile. Okay, this looks good. Option, Animate. Let me go ahead and then click Play. Here's the water surface. Oops, this is faster, I think. Yeah. All right, pretty boring, but it looks like it's stable now. Let's go ahead and check out that current number, which was what I'm really after. So View, Unsteady Flow, Spatial Plot. And now I'm going to change the variable to the channel current and then click the play button. Okay. So now it increased. Hold on. Where did it start? Yeah. So it started down at like 0.2, maybe 0.25. And then instead of going up to 2.4, I expected to go up to about 1.2. So that's 0.8, 0.9. Don't worry about this last cross section here. There's 1. Okay. And it looks like it's finishing off the simulation right around 1.2. Okay, I closed my Irfan view, but this is where I got the equation, just ChatGPT. We doubled the spacing so that halved the current number. If we wanted to decrease the current number more, let's go ahead and just decrease the time interval. And right now we're using 1 minute, but we can change that to how about 30 seconds. So I'm going to go run and then unsteady flow analysis. Instead of 1 minute here, let's go ahead and change that to 30 seconds. By the way, I can also change this 30 seconds. It's the same number that you'd see if I go computation interval, advanced time settings. It's this same dialog box right here. Now, I didn't save it, so I think that's why it didn't change. But if I change this to say something like 10 minutes and then clicked OK, it should be, hold on. It now says, oh, I thought that's going to change over here. Well, it did for me before. Anyway, let's go ahead and keep this at 30 minutes, at 30 seconds, save the plan, and then click compute. All right, that's successful. Let's go ahead and close that. Now let's take a look at the current number. So I'm going to go View, Unsteady Flow, and then for the variables, we'll use the current number and then click play. So it's going to start off at about 0.1 and then increase 0.2, 0.3. I expect it only to get up to about 0.6 because remember, the final current number was 2.4, but then we halved it by doubling the spacing between cross sections. Now we're going to halve it again by decreasing the time step. Okay, I'm near the end of the simulation, and sure enough, it ends at 0.6 for that current number. Now, say for instance, you don't want to have to manually change the cross sections or manually change the time steps. That's where the advanced time step controls come in. Before I get to that, I'm going to go ahead and change the cross sections back and the computation time interval back to 1 minute. So let's Tools, Cross Sections. Let's delete, and then Tools, Cross Sections, 500 feet, interpolate, and close. Okay. File, save, Now back to our unsteady flow data. I'm going to change this back to 1 minute and then File, Save Plan. Another way to get to that advanced time control tab in that dialog box is to click this ellipse button right here next to computational interval. And then boom, it takes you directly to advanced time step control. That's what I meant to say. All right, right now we're using 1 minute, but the time has changed. We're going to use advanced time step based on the current number. So what I'm going to do is I'm going to set the maximum current number to 1. Boom. If the maximum current number is exceeded, then the time step will cut in half for the very next time interval. Because HEC RAS uses an implicit solution scheme, current number can be greater than 1 and still maintain a stable, accurate solution. I'm going to use 1 though, but what we also have to do in this box here, the maximum number of halving base time steps, is to say the number of times it's allowed to halve. So right now it's 0, which means 60 seconds is the smallest time interval that it can be achieved. If I type a 1 in here, we get 30 seconds. If we have it twice, that's down to 15 seconds and so on. Okay. The other numbers here about like a minimum current number, I actually do need to type something in here. I'm going to type in 0.4. It has to be less than half of the maximum. And that's basically the opposite situation where you would double the time interval. Okay, but we're not doing that. Okay, let's go ahead and see what happens here. What I suspect will happen is the time interval will start at 1 minute. And then once the current number gets up to 1, the time interval will half down to 30 seconds. And then once that current number, so the current number will be 0.5, it'll increase again up to 1. And then the halving operation will happen once again. And then our final time step will be 15 seconds. All right, so let's go ahead and click OK. I'm going to go ahead and File, Save Plan. Now down here in the notes, we have a new message that says time step is controlled by the current condition. So I believe it'll still start at 1 minute time step, but then it will be controlled by the current condition that we set. And compute. Okay, so it looks like that ran. Looks like we do have some instability here, just like our first model run. And if I scroll up far enough, I saw some green text that looks like it's keeping track of the time step. So it starts off at a 1 minute time step, but then on January 1st at 4:49, it halved. So it switched down to a time step of 30 seconds. Oh, I'm sorry, it was 4:49 a.m. The following day at 6:57 a.m., it halved again and it went to 15 seconds. All right, let's go ahead and look at those results though. I'm going to go View, Unsteady Flow, Spatial Plot, and then for the variables, let's turn on the current number and then click. So it's going to increase up to 1. Right there's when it halved. You can watch the video back, but it was up to 1 and then boom, it went down to 0.5. Now it's climbing again because the total number was originally 2.4. We should expect it to get up to 1.0 once again. Okay, it's approaching 1.0 again. We know it's going to happen at 6 a.m. It's 4 a.m., 5 a.m., any moment now. There it goes. All right, very cool. So this is the current number, and it's going to increase probably to about 0.6 is my guess. All right, the last option I want to demonstrate is the time series control. So let's go back to our ellipse button here. And instead of adjusting the time step based on current, I'm going to click on this next one down here, adjust the time step based on the time series divisors. So our simulation starts on January 1st, 2020, and then space 0, hours. And I'm going to have a divisor of 1. So basically it's going to start at the original time step, which is 1 minute. Then what I'm going to do is paste. Okay, cool, that worked. Let's see, how about at noon of that day, we will use the divisor of 2, so that then the time step will be 30 seconds. And then let's go ahead and say at the beginning of January 2, that's when we will half once again. So we're doing a manual halving. I could use different numbers than powers of 2, but I'm just going to go with it. And then after that, it will just continue with a 15-second time interval because we're using a divisor of 4 here. All right, let's go ahead and run the same simulation and then look at the results. This time it says the time step is controlled by time series of divisors. That's true. I'll go File, Save Plan, and Compute. Okay, it looks like we still had some instability there, but that's all right. What we're focusing on here is that current number, unsteady flow, spatial plot. Here is our plot. All right, so for variables, let me go ahead and turn on the current number and turn off water surface elevation, and then run the simulation. Now I know exactly at 12 noon, that's when the current number is going to half, and it looks like we're already past 1. That's fine. 10 a.m., 11 a.m. now. Okay, so it dropped down from about 1.5 to about 0.75, I believe. And it's going to happen once again, and that's going to happen at midnight at the beginning of day 2. That's 10 o'clock, 10:30, 11 o'clock, 11:30, right about then. Okay, so it went from about, what was that? About zero point 0.9 down to 0.45, I think. A few other things I wanted to point out. Another option for results that became enabled is this unsteady flow time series plot. I'm not a big fan of this simply because I can't read the axes, but what we saw here for the variable, I think this is water surface profile again. Yeah, we could toggle that off and turn on current number. And oh, this is pretty interesting actually. We could see how it ramped up and then it halved, it ramped up a little more, it halved, and then went unstable. And I know there is an option here to turn on or to size up the font, but I've tried all of these and none of them seem to work for the actual values. If I toggle all these font sizes on, it does increase this font size, but not the actual font size of the time and the current numbers. So that's a little frustrating. I'm going to change that back because it affects all the plots, not just this one. But it's a cool plot nonetheless, and that's worth pointing out. If you're interested in more, there is a page in the user's manual talking about unsteady flow simulation options, but you have to scroll down a ways to this advanced time step control tab before you get to the actual content of what was covered in this exercise. Well, that's it for this exercise. What we did was look at the current number and then change it based on changing the values of dt and dx both manually, and then also dt with respect to using the advanced time step controls in HEC RAS.